The discussion on two-factor factorial we had so far can be extended to the general case where there are A levels of factor A, B levels of factor B, C levels of factor C, and so on. Now, with n replicates, we would have the number of observations equal to the product of all the levels A, B, C, and so on, and the number of replicates. Now, remember that if all possible interactions are to be included in the model, we need at least 2 replicates to determine the sum of square due to error. We can use the ANOVA to formulate and test the hypothesis about the main effects and the interactions. Now, extending to 3-factor factorial, for example, the ANOVA equation for the fixed effects model would look like this. Yijkl is equal to mu plus tau I plus beta j plus gamma k plus the interaction terms, as you can see here. So you have 1, 2, 3, and 4 interaction terms, 3 for the 2-factor interaction and 1 for the 3-factor interaction, plus error. So as you can see here, as suggested by the indices, okay, you have A levels, B levels, and C levels for factors A, B, and C respectively, and you have n replicates. Now, the total sum of squares is computed using this equation. Okay, here it looks very familiar to you by now, while that of the main effects are computed as such. Okay, and of course, all of these computations can be done through statistical softwares. Okay, so in computing the total sum of squares, you can see here basically the sum of the squares of all the observations minus the square of the grand total divided by ABCN. And then for the sum of squares, you have again the familiar equations. Okay, so for example, for sum of square of A, it's just equal to 1 over BCN times the sum of all the squares, okay, of the totals for each level of factor A minus the square of the grand total divided by ABCN, and so on. Okay. Meanwhile, these are the equations for the 2-factor interaction sum of squares. Okay. And then the 3-factor sum of squares is computed using this equation. And again, you have here a subtotal. Okay, you will need the subtotal here, okay, which is just equal to these two terms here. All right. And you will need that subtotal, sum square subtotal, to compute for the sum of square of error, okay, which is equal to the sum of square total minus the sum of square subtotal. Using these equations and the familiar equations for getting the mean squares, okay, you can then summarize your ANOVA table for the 3-factor factorial as such. So again, you have your sources of variation in the first column. You have the 3 mean effects. You have the interaction effects for 2-factor and the 3 factors. And then your error and of course your total. And these are the sum of squares that can be computed using the equations I showed before. And of course, they are found in Montgomery. And then you have the corresponding degrees of freedom in the third column. And the mean square, as you know, is just equal to the sum of square divided by the degrees of freedom. And then you have here also a column showing the expected sum of square, expected mean of square, I should say. We will make a point on that later. Okay, and of course, you have your F naught, okay, which is computed as the mean square of the factor you are interested in divided by the mean square of the error. And if this is large, as you know, then it signifies that the source of variation is significant. Okay, so let's look at this example, the soft drink bottler example, as an example of the application of the fixed effects model for 3-factor factorial. Okay, so the problem reads, which is actually from Montgomery. A soft drink bottler is interested in obtaining more uniform fill heights in the bottles produced by his manufacturing process. The filling machine theoretically fills each bottle to the correct target height, but in practice, there is variation around this target. And the bottler would like to understand the sources of this variability better and, of course, eventually reduce it. Now, the process engineer can control three variables during the filling process: the percent carbonation, which can be denoted as A, the operating pressure in the filler, denoted as B, and the bottles produced per minute or the line speed, denoted as C. The pressure and speed are easy to control, but the percent carbonation is more difficult to control during actual manufacturing because it varies with product temperature. However, for purposes of an experiment, the engineer can control carbonation at three levels, namely 10, 12, and 14%. She chooses two levels for pressure, which are 25 and 30 psi, and two levels for line speed, which are 200 and 250 bottles per minute. Now, she decides to run two replicates of a factorial design in these three factors, with all 24 runs taken in random order. The response variable observed is the average deviation from the target fill height observed in a production run of bottles at each set of conditions. Now, the data that resulted from this experiment are shown in the following table. Okay, positive deviations are fill heights above the target, whereas negative deviations are fill heights below the target. And then the circled numbers in the following table are the three-way cell totals YIJK. Okay, so let's look at the data, the observed data. So here on the rows, you have the percent carbonation, your factor A. Factor B, the operating pressure, okay? This here, okay? And then you have your line speed, okay, at 200 and 250. Your operating pressure are at 25 and 30 psi, okay? And as mentioned earlier, the circled and circled numbers are the three-way cell totals, okay? Three-way cell totals. So -4 here is the total for observations for level I of factor A, level J of factor B, and level K of factor C. And these observations are -3 and -4, okay? And so on. And then, of course, you have here the row totals, okay? So -4 here is basically the sum of all observations for 10% carbonation, okay? 20 is for 12% carbonation, and 59 for 14% carbonation. While you have here the BC totals, so observations at J level of factor B and K level of factor C. All right. So for example, here 6 is the total for 25 psi and 200 bottles per minute. So that is -4 plus 1, -3 plus 9 equals 6, and so on. For yi ... here, that would be -4 plus -1 plus -1, that's -6 plus 2 equals -4, and so on, okay? And then you have y, in the last row, you have y.j ... which are basically the sum of observations under level J of factor B. So for example, 21 here is the sum of the observations at 25 psi. So that would be -4 plus 1 plus 9 plus -1 plus 3 plus 13. And you can apply the same thing for 54. And you also have here the grand total, okay, of all observations, which is basically the sum of all these things, okay, of all your observations. So that is 75. And of course, you have your AB totals and your AC totals. So these are the sum of observations for the AB totals for level I of factor A and level J of factor B. And then AC totals for level I of factor A and level K of factor C. Okay, so you get that here. And so now we can compute the sum of squares. So for sum of square total, again, you have the square of each observation and get the sum of all of those. That would be 571. Grand total is 75, so 75 squared divided by A, which is 3 times 2 for B times 2 for C. Okay, so 3 times 2, 6 times 2, 12 times you have 2 replicates, so you have 24. Therefore, this is equal to 336.625. And then we can just apply this the formula or the equations that we have for sum of square for each factor and the interactions to get the corresponding sum of squares, as shown here. Okay. So this one is the sum of square for the AB interaction. For the AC interaction, please feel free to pause the video and compute for these values on your own. You have for the BC interaction, the ABC interaction. And then, of course, you have your sum of square subtotals. Okay, this is also an equation that has already been shown. So now you can use that and sum of square total to compute for the error sum of square, which turns out to be 8.5. Okay, and of course, statistical softwares are available to do these computations for you. Now, summarizing all those numbers, okay, you have your source of variation here, and then the sum of squares, and we just also include the degrees of freedom. And then compute for the mean square, which is sum of square divided by degrees of freedom. And then you have your F naught, which is equal to mean square of the factor or the interaction divided by the mean square of error. Okay, so you get these numbers here, and these are the corresponding p-values for these values of F naught. Now, based on the computed numbers, we can see that all three main factors or main effects are significant at 5% significance level. While if we look at significance level of 10%, we can see that the AB interaction is also significant. The rest of the effects are not significant, which means to say that the data supports the null hypothesis that the effects, okay, these effects are equal to 0. Okay, now we can see on this graph that as we increase the levels of carbonation, pressure, and the line speed, okay, the average field deviation increases. Okay, it can also be observed that the interaction of carbonation and pressure, okay, further amplify this relationship, although not by much, no. And that means that higher deviations can be observed at combination of high level of carbonation and pressure. Now, this therefore means that to reduce the filling deviation, it is desirable to set the percent carbonation at 10%, pressure at 25 psi, line speed at 200 bottles per minute. However, since it is also desired that production rate be maximized, and we can see that the difference in average field deviation is not as large for different line speeds, it can be recommended that that the line speed of 250 bottles per minute can be adopted. Now, carbonation is not completely controllable in practice, and say that the current distribution is followed by the flatter normal curve shown here. So this one. okay, you can see that the average field deviation at the recommended high speed, okay, this one, the high speed and low pressure increases dramatically towards the right end of the distribution. So here, this is the curve for high speed. This is the curve for average field height deviation at high speed and low pressure. And as you can see, it increases dramatically as the percent carbonation increases. Now, to minimize this occurrence, what can be done is to improve the process such that the standard deviation be minimized. Okay, so we want this dashed line instead of this flatter one. Okay, we want to minimize the standard deviation, okay, while targeting for lower carbonation levels so that we can stay within this range of average field height deviation. Okay, again, it has to be pointed out that you should always perform model adequacy checking. And for this example, actually, if you perform residual analysis, you can conclude that there are no serious errors with respect to the assumptions of the model. Okay, now let's quickly go through fitting response curves and surfaces. Okay, so as I mentioned before, ANOVA treats factors as though they are all qualitative or categorical. No, response curves can be used to fit a quantitative factor to the response in order to have an equation that relates the response to the factor. And response curves can be used to interpolate, okay, that is, predict the response at the factor levels between those that were used in the experiment. Response surfaces work in the same manner when dealing with at least two quantitative factors. And linear regression methods are used to fit models to observe for these quantitative design factors. Okay, now let us go back to the battery design example. In this example, one variable, which is temperature, is quantitative and it has 3 levels. So we can use linear regression to investigate the linear as well as quadratic effects of temperature to battery life. Okay. So in this output, it is assumed that temperature is quantitative while material type is qualitative. So as you can see here, our p-values, okay, for the main effects are less than 5%. So this signifies that the main effects are significant at 5% significance level, whereas a squared and ab are not significant, while a squared b is significant, okay, because we have a p-value of 0.01 here. Okay, so at 5% it is significant. The r squared of the model is rather high, okay, and so we can conclude that the model is sufficient in explaining the variation in the response variable, which is battery life in this case. And this also means that at least one of the terms, okay, is significant. And it turns out that it's a, b, and a squared b. However, according to the hierarchy principle, a model should include lower order terms that compose a high order term in the model. So if we deem that a squared, well, it is shown here, okay, based on the results, a squared b is significant, so we want to include it in the model, right? But with the hierarchy principle, okay, if we include a squared b, the model should also contain a squared and ab, which are the lower order terms. This is a partial design expert computer output. Okay, the first part of the computer output is found in page 212 of Montgomery. But since regression modeling is not yet the focus of this particular lecture, this is not explained in detail here. I just show you here the final equation in terms of the actual factors. Okay, and this is the predicted life as a function of temperature for the 3 material types. Okay, and this is for the battery design example. Okay, so this is your response curve corresponding to the model that we have derived. Now let's look at another example, okay, for response surface. This is a tool life experiment example. Okay, so the effective life of a cutting tool installed in a numerically controlled machine is thought to be affected by the cutting speed and the tool angle. 3 speeds and 3 angles are selected, and a 3 to the 2 factorial experiment with 2 replicates is performed. The coded data are shown in the following table, and the circled numbers in the cells are the cell totals. Okay, so cell totals are encircled. So you have 1, 2, 3, okay, 3 levels for total angle, okay, in degrees, and then 1, 2, 3 levels for cutting speed in inches per minute, okay, and of course you have here the row totals, the column totals, and the grand total, okay. And this is the output for the classical ANOVA, which means that both factors are treated as categorical variables. And as you can see, there seems to be no problem with the assumption of normality. And then your R squared is quite high, 0.8895161. Okay, and then you can see here that based on the p-values, your angle, your speed, and the interaction between angle and speed are all significant. Okay, and the residual plot doesn't show any particular trend, okay, which means, again, that the model is acceptable. Okay, now since the factors are quantitative, both angle and speed are quantitative, okay, we can use a second order model, okay, to fit the data, and the second order model can be as such. Okay, so you have beta, the added terms are beta 11 x1 squared plus beta 22 x2 squared. Now comparing to the classical categorical ANOVA, the second order model is a poorer fit. As you can see in the graph of the total life, the observed total life and the predicted total life, okay, and the R squared is much lower than that of the classical ANOVA. Okay, as you can see here, it's 0.46 compared to the almost 0.9 R squared in the previous model. Now, part of the reason for this is that only one of the 4 degrees of freedom for the interaction was present. So this was the only one, no? Only one interaction term, okay, which was included in the second order model. The other interaction terms, okay, include the following. So you have B112 x1 squared x2, B122 x1 x2 squared, and then B1122 x1 squared x2 squared. Okay, and in the second order model where we only have one, we only included one in the 4 degrees of freedom of interaction, okay, we can see that based on the results of the ANOVA, okay, only speed is significant, okay, in the model, all right? Okay. And now this function in JMP, which is called the prediction profiler, is a very useful function for optimization. Now this graph shows us the optimal values for each factor corresponding to the second order model that we just investigated. This means that the optimal value for angle would be 20 degrees, that for speed would be 166, and then this provides the desirability, okay? Now, this is the output for the second order model with the additional higher order terms. So if these three were added to the second order model, you will see that the R squared and the adjusted R squared are significantly increased. And the actual versus the predicted response variables, values of the response variable fit better, okay? And then if we investigate the p-values of the different terms, okay, we can see that more terms are actually significant. So you have your angle, you have your speed, and then you have interaction between angle and speed, okay, etc. Okay, so this one shows the sorted parameter estimates, okay. So again, you have angle, the interaction between speed and angle. You have speed also, okay. And based on the prediction profiler, these are the optimal levels, okay, for angle and speed. So for angle, it's 25 degrees, and for speed, it's about 150 inches per minute, okay. And this is the corresponding 2D contour plot of tool life response surface, okay. So these are the constant tool life contours, okay, at different combinations of speed and tool angle, okay. And this is the corresponding, okay, so this should be response surface. This is the corresponding response surface for our model. All right. Now, sometimes it is not feasible to completely randomize all the runs in an experiment. This is true in the case of nuisance factors. Okay, so suppose that we are confronted with a nuisance factor. Say a different raw material is required to run each replicate in an experiment. We need to use a model to represent the nuisance factor. In this case, the raw material with blocking. Okay, so the model then becomes, so instead of this model, the model then becomes like this. Okay, so delta K represents the effect of the kth block. We run a single replicate of a complete factorial experiment in each block. And note that within each block, treatment combinations are still completely randomized, okay? And it is assumed that interaction between blocks and treatments are negligible, okay? And the error term, which is epsilon ijk, actually includes the interactions, okay, which can be denoted as such. Okay, so they're all captured by the error term epsilon ijk. Okay, so now if we summarize, okay, the ANOVA for a two-factor factorial in a randomized complete block, okay, it would look like this. So again, you have your sources of variation, you have your sum of squares, okay, and then you have your degrees of freedom and expected mean square, okay. You will notice here a new term, sigma, okay, sigma squared sub delta, okay. So this is the variance due to the block, and this is equal to ms blocks, okay, mean square blocks minus mean square error divided by the product of A and B, which are the number of levels for factor A and B respectively. Okay, so let's apply that in an example. Here we have the radar scope target detection example. So it reads, again, this is from Montgomery. An engineer is studying methods for improving the ability to detect targets on a radar scope. Two factors she considers to be important are the amount of background noise or ground clutter on the scope and the type of filter placed over the screen. Now, an experiment is designed using 3 levels of ground clutter and 2 filter types. We will consider these as fixed type factors. The experiment is performed by randomly selecting a treatment combination, so ground clutter, level, and filter type, and then introducing a signal representing the target into the scope. The intensity of this target is increased until the operator observes it. The intensity level at detection is then measured as the response variable. Because of operator availability, it is convenient to select an operator and keep him or her at the scope until all the necessary runs have been made. Furthermore, operators differ in their skill and ability to use the scope. So consequently, it seems logical to use the operators as blocks. So the operators are actually nuisance factors. 4 operators are randomly selected. Once an operator is chosen, the order in which the 6 treatment combinations are run is randomly determined. Thus, we have a 3/2 factorial experiment run in a randomized complete block. Okay? The data are shown in the succeeding table. Okay, so the relevant ANOVA equation would therefore be like this, okay, where tau I represents the ground clutter effect, beta J represents the filter type effect, tau beta ij is the interaction between ground clutter and filter type, and delta K is the block effect, and then of course you have your error ijk, epsilon ijk, and epsilon ijk, your error, is normally and independently distributed with mean 0 and variance sigma squared. Okay, and as mentioned in the problem, there are 3 levels for ground clutter, and then you have 2 levels for filter type, and you have 4 operators, so you have 4 blocks. Okay, and these are the observed values, okay, for intensity level at target detection. So you have your rows for the first factor, which is ground clutter, and then you have your filter type, 2 filter types, and you have 4 blocks, the operators 1, 2, 3, and 4. Okay, now given those data, we can now use the sum of square equations to compute for the sum of squares. Okay, and for the sum of square of blocks, okay, using this equation, we get the value to be 402.17, and the variance for the block, okay, is equal to 20.5. Okay. Summarizing the values in our ANOVA table, we get this. Okay, and of course you can get these numbers using any statistical software of your choosing. Okay, so according to the p-values, we can see that ground clutter, filter type, and their interaction are all ground clutter and filter type are significant. The interaction of the 2 main effects, okay, is also significant, but at 10% significance level. Okay, now suppose that only 6 runs can be run per day, okay, and observation day, and so if we can only make 6 runs per day, okay, observation day becomes a second randomization restriction. Okay, now further, we have a different operator per observation day. Okay, so here we have to use a p by p Latin square design. Okay, for our problem, it will result in a 6 by 6 Latin square design. How is that so? So say you have Fi, which is the ith level of the filter type, and G sub j, the jth level of ground clutter. Okay, so you have low, medium, and high for ground clutter, and then filter type 1 and 2 for the filter type. Okay, so you have 2 times 3, okay, 2 times 3, which is 6. Therefore, you need 6 by 6 Latin square design. Now, the Latin letters would correspond to F1G1, F1G2, F1G3, and then F2G1, F2G2, and F2G3 for A, B, C, D, and F, D, E, and F respectively. Okay, and the model or the ANOVA equation will look like this. Okay, so yijkl is equal to mu plus alpha I plus tau j plus beta k plus tau beta jk plus delta L plus epsilon ijkl, where tau I or tau j is equal and beta k are effects of ground clutter and filter type respectively, and alpha I and delta L represent the randomization restrictions of days and operators respectively. Okay, and your Latin square, for this example, these are the observed values for this Latin 6x6 Latin square experimental design. Okay, the observations, of course, are run in a completely randomized manner. Okay, and the operators will have to perform the experiment 1 time per day. Okay, and these are the sums of the observations. So these are the cell totals. Okay, you have the column, you have the row totals, and then you have the column totals, and of course you have the grand total. Okay, now if we summarize the values for the sum of squares, the degrees of freedom, and the mean square, as well as the F and P values for the different sources of variation in the ANOVA table, it will look like this. Okay, and this table just includes the general formula for degrees of freedom for the sources of variation. So the sources of variation include your main effects, your interaction, and then you have your blocks, which are days and operators for this example. So that's it for this lecture. So far, we have covered the following topics. First, we talked about the advantages of factorial design. And then we talked about the fixed effects model for the two-factor factorial, for general factorial, as well as those where we need blocking. And then you have, we also talked about the regression model briefly, as well as response surface and contour plots, and of course, blocking in factorial designs.